All right. Welcome, everyone. Nice to see so many of you here. My name is Viktor Klang, and I'm an architect in the Java platform group at Oracle. And my reason for being here today is to give you a bit of a recap on what's happened most recently, but also a quick look into what's coming down the pipeline. So, all right. So, since the world shut down circa 2020, we've delivered quite a few features. And while it might be tempting to just look at these features in isolation and see if they are things that work for you, there are some more higher level trains or higher level feature arcs behind this. So I'm going to go into a bit of detail on how these things fit together. Because if you look at language features from how can I use this specific feature? And if you were to design language feature from that perspective, then I think in the end, everything would sort of look bolted on because there wouldn't necessarily be that much of a nice interaction or a logical flow between features. So these are some of the features that we've released, and some of them are in what we call preview status. And importantly here, preview for us is still production quality. But it is a window of opportunity for you to provide feedback on how we could make it better, or if it's just right. So I would encourage you to take a look at the preview features and provide feedback while this window is open. We love that kind of feedback. So one of the most recent changes that have been made with how we develop and release Java is we do these 6 months cadence releases. And that means that you have to break features down into smaller, more distilled components, because otherwise you would create something and you wouldn't necessarily know when you would be able to release it, because it's just really hard to reason about. I mean, we all know this as developers, right? The bigger and the more complex the project, the harder it is to try to figure out when it's ready. So a good side effect of this is that we can now more targetedly distill features into multiple components and even deliver features incrementally. So a quick recap here. Records. How many of you have used records? Oh, for all intents and purposes, probably like 80%, right? It's a model of a nominal tuple. Are you familiar with tuples in other languages, like more structural representation of data? It's an immutable carrier, and it specifies this sort of aggregate. In this case, we have record point, and we have an x and a y coordinate represented as ints. What we can do when we have this information and with the semantics that we've equipped records with is that we can derive things. We can derive equals methods, we can derive hash codes, we can derive functionality based on the specification of the thing. And of course, it's possible to override some of these capabilities within some constraints. The good thing here, though, is that a record is more like a class. It can implement interfaces, and it can have type parameters and other things that you're used to. So it's not something completely distinct in and of itself. It doesn't exist in isolation. So while records reduce boilerplate, it's not really about the boilerplate at all. Because when you can reason about things, it's much easier to do what you're supposed to do. So the boilerplate reduction here is due to the fact that we know specifically more about a record than we do of a typical class. It has more semantics attached to it. And most records tend to become one-liners. Typically, if you want to represent somebody, you can just write a single line of code. Interestingly, if you're familiar with Java serialization, it treats records or record instances separately or more specifically than it does typical classes. Because all creation of records go through the canonical constructor. You actually avoid some situations where the typical Java serialization would allocate a plain memory segment of that object and sort of stuff the individual values into that. But in this case, with Java serialization and records, we actually need to deserialize the components and pass the components into the constructor. So there's no risk of having these sort of partially initialized objects. So what aren't records? So before we developed records, people would ask for tuples. And tuples are great if you have a structural type system. But Java's type system isn't structural. So how do we deal with that? Well, we think that names carry more semantic meaning about the program. Because if all you have is structure, then you might think that things are equal or the same because they have the same shape, but they might be intended for completely different purposes. So by having names, it becomes more apparent. We spend more time reading code than we do writing code. So making it easier to read the code and understand the code has more value than just being able to write the code. So by having names, it's easier to review and it's easier to learn a piece of code. So we have sort of the same story when we introduced lambdas. So instead of adding structural function types to Java, we introduced nominal function types. And we made it possible for others to declare their own function types. So you can declare your own functional interfaces. And records are not a syntax generator. It's not about writing less and have more code be generated as a result of that. It's about being able to represent data as data. So there is a really strong contract between a record and itself. So if you create a record by providing parameters to the constructor, you're able to get those values, since records are immutable and they have accessors for those components. You can create a record instance and then extract the individual values from the accessors and feed that into its own constructor and get something that equals itself. So there's a strong contract between how it was created and how it can be recreated. Beyond records, what we've also delivered is sealed classes and interfaces. So how many of you are familiar with sealed interfaces and classes? Okay, how many of you have been using them as a part of modeling your logic? Cool. I hope to be able to demonstrate some of the benefits of doing that. If you sort of squint, you can see this as a generalization of finality. So if you add final on a class, you're saying that this is the only type here. It cannot be extended. This is the one. Sealing is about saying that these are the permissible implementations, not this. So it's more powerful in that sense. So when you declare an interface, you can say that it's sealed, and you can also optionally specify which implementations are permitted to implement this interface. And of course, if you don't add an explicit permits clause, it's all the subtypes of this thing within the current compilation unit. And that can be helpful when I'll show you an example later where adding the permits clause might not necessarily make sense. All right, so what's the point? Okay, so now we can specify a more constrained domain or constrained permutation of inheritance. But I think the important piece of information here is we can be specific about the knowledge. We know exactly that if I have this, it can be either this or that. And knowing what it cannot be is very useful information for you as a developer as well. And there's a nice benefit to this as well. When we have the sealing information, we can use that sealing information in the compiler, because now the compiler also knows more. And from a library developer point of view, you can expose interfaces that you don't have to worry about users implementing. So you're able to have an abstract interface and be able to control the exact implementations thereof. So why is this important? Well, if you combine this sort of separate record component or record feature with the sort of separate sealed classes feature, you get algebraic data types. And you can think of records as product types and sealed classes as sum types or discriminated unions. And they are pretty expressive when it comes to data modeling itself. And in some languages, that's the only means of abstracting data. And what's nice about this is if you look at this, example here, we have some sort of expression type, and we say that we have 4 different kinds of expressions. So we have a sum that has a left and a right expression. We have a product expression that has a left and right expression. We have a negation expression, and we have a constant expression. So that is our sort of full data domain in this case. And we've essentially said that, so the expression interface is sealed. So these are the only implementations of expression. And how can we use this? Well, first of all, are you familiar with pattern matching in Java using this more enhanced instance of check? So we call this a type pattern. And if you've been writing code, you've typically written the code on the left quite a few times. You want to test if something is an instance of some type, but typically the reason that you do that is because you want to use that information. You want to cast it. So now you have these 2 things that are related, but they are in different lines. So you might actually copy-paste some code, change it in one place, forgetting the other, and then it blows up at runtime. So what we introduced was being able to say, do all of the things. Do the type check and the cast, and introduce a named variable that is in scope where this makes sense. So now these 3 things cannot drift apart. So this is more of an elimination of defects than it is making having you write fewer lines of code, right? So interestingly, most things in Java are block-based or square-shaped in a sense. They exist within the declared braces. But in this case, these pattern bindings are flow-based. So they are available where they make sense logically. So if you look at the example above, then we're checking if X is an instance of a string, and if it is, then S in this case is in scope, because the only reason or the only way that you could get to that part of the logical expression is if the former was true. So now you can say that, okay, so if X is a string and that string's length is greater than 0 as a single logical expression. So it's in scope where it would be definitively assigned, but it also follows all of the logical flow control operations. So a more advanced example to the left or at the bottom of this is if you have some conditional that says if it isn't a string or the string length is less than 0. So either it's not a string, or if it is, it has to have a length equal or less than 0. So S is not in scope in the braces, but in the else clause, the only logical reason why you would end up there is if it is a string or if its length is greater than 0, in which case it's also a string, right? So S is in scope in the else block. And you wouldn't probably notice this because it just works. And if we didn't do this kind of flow-based scoping, then simple refactoring tools like invert conditional and stuff like that wouldn't work because you would end up with a program that would complain. All right. Yeah, go ahead. Go back. What? So what would the... So you, as a statement, just say X instance of string S. Not right now, but you might be in the future. We'll see. We'll see. It's an interesting topic. We can talk about that later. Okay. All right. So how do these two things intersect? Well, for records, you have more sophisticated pattern matching. So not only can you check a specific type, but you can also check the structure. So since records define a specific structure, you can now introspect that structure as a part of your conditional. So let's say that we have this record circle that has a point center and an int radius. Now we can write an if statement saying, if the shape I'm looking at is a circle with this point center and int radius, now I have the variables center and radius available within that block. And those have the values of whatever the circle shapes values were. And it's not a coincidence that if you look at how it's declared and how it's being pattern matched, they are almost identical, right? You see the construction and deconstruction are inverses of each other's. So you can also use type inference. So if you don't want to repeat yourself to know what the exact type is, in this case, it can only be a point. But if you want to infer the types, you can use var instead. All right, so let's make this more sophisticated. Well, so if you have this point that the circle had, and you create this new circle with that point, you can also recursively decompose it. So not only do you say that the circle has a point, but I want to be able to extract the x and y out of that point. And you can do that in a composite pattern match. So now you have both cx, cy, and r pointing to the values of what was in that shape at that time. And now you can use them. Interestingly here, right, you're essentially making a query on top of structure, if you think about it like that. You're saying that if this structure has this shape, then I am going to extract the different components out of that. And either the entire thing succeeds or it doesn't, right? So this conditional, if something here didn't match your query in this sense, then you wouldn't enter into that if block. Yes? If you can do the deconstruction inside a lambda, like I think you actually need, so I guess your question is, can I pass a pattern match as a lambda? Yeah. You would still have to declare the type of the parameter, and then you would do the arrow, and then you would do the deconstructuring. But the thing is that it's a part of a logical expression, right? So let's say that it's a predicate lambda that you're passing in, something that is supposed to evaluate to true or false, then you could do something like this. All right, so, and a small but important new feature, if you want to completely ignore pieces of the structure, you can use an underscore to say that something will be here, but I don't care about what that is. It's not a part of something that I need. Okay. So if we have these ADT, algebraic data types, and we want to use that, how do we do that? Like, we have the structure that we defined before, but we didn't really define any methods that do stuff. So typically, when you create an interface, you would define and you would decide which methods make sense on the interface. And sometimes those things might not necessarily make sense for all uses of that interface. So in this case, we could actually add new functionality outside of the interface because we see the structure. We can introspect the structure of the domain. So let's say that we want to implement a evaluation method. We would have an expression passed in, and we would then switch on that expression, saying that if it's a sum, then evaluate the left and the right-hand side and add those two together. If it's a product, you evaluate the left and the right-hand side and multiply them. If it's a negation, you negate the evaluation of the expression. And if it's a constant, you just return the constant. So, and I think many of you have probably seen this before, either as a part of your education or as a part of your work. So it's a simple example, but it showcases how you can add behavior outside of the domain itself, because that method could live anywhere. It's completely unrelated to the internals. Let's make it slightly more advanced. The point here is not about understanding differentiation of expressions. So it's not really about that. It's more about the ability to say that if differentiation appeared as a need after the fact, I can add that after the fact and outside. And perhaps you didn't think about that, but in the previous slide, there's no default case. Right? Because the compiler knows that there are only 4 different types. So it will say, oh, I know that this covers the complete domain of this thing, and there's no situation in which case there would be something that could fall through and blow up, right? So by adding the sealing information, not only were we able to write less code and not have to write case default, throw illegal state exception, shouldn't happen. It's one of the more common exceptions when you don't know what you should do, right? So by having the sealing information, we also had to write fewer lines of code, but also if we ever add a new expression here, a new type of expression, if we did add default cases in all of our usages, then they would be silently broken, because they wouldn't know about this new thing that we introduced. So that would hit the default case, and then you would have silent blow up somewhere else. So it would instead give you a compilation error saying that, hey, the information you had before is not true anymore. There are no more cases that you need to consider. So it's actually a way to avoid having to debug some gnarly things in production. So why are we doing this? Well, essentially, we want to be able to model data as data. Sometimes all you need to model is data. And classic object-oriented program is really good at modeling complex domains and large programs or applications, because you get these benefits of being able to defend different kinds of boundaries within your system, whether it's visibility into things or compilation, separate compilation, versioning, security boundaries. So many different things that could exist within a program. Now you have a means of actually being able to enforce those boundaries within your program. But also, we live in an age where we're writing smaller and smaller programs. So 10, 15 years ago, if you were writing a huge application that ran as a single process, you're more likely today to write smaller programs that communicate, either via HTTP or messaging, or may it be. But since the size of the application itself is getting smaller, the sort of size of the application to the boundaries of the application now changes. So now it's more about, okay, how do I interact? Typically you get some JSON payload or some XML or Avro or Proto or whatever you're getting, and you need to be able to parse that, you need to be able to translate that into your domain and then do something, and then in reverse sort of convert it to some other payload. So being able to better model the data also makes it easier for you to get the most out of this smaller application envelope. And of course, when it comes to communicating programs, that's almost always data. Almost always data. So the boundaries that we need to defend against have moved, right? We're doing different kinds of applications today in general. And modeling this sort of simple data, whether it's a customer or an order or payment or whatever it might be, becomes slightly more cumbersome if you need to do the entire OO thing. But if you want to be able to map the external representation to the internal representation, perhaps a record is a very nice way of just saying that, hey, this is the thing that is represented like this on the wire. So having records, but also pattern matching, also makes it more possible to say, okay, so I parsed the information that I got, I converted it into my own domain, and now I can query that domain given pattern matching. So there's a flow of work where it goes from the wire representation to the internal business rules. All right, so to sum this up, what we're trying to do is to just let data be data. And data should be immutable, ideally, right? Data should be typed, so we don't just pass around strings or objects. And it should be consistent, right? So that we know if we have the data, it makes sense. And it would be nice if we were able to create the data easily and also convert it to something else easily. And also, all of these things, they sort of conspire to reduce the need for these sort of boundary checking as a default thing, right? So, in my experience, doing this also makes the program more testable because it's more clear what the entry and exit points are. So instead of having to do a lot of mocking, for instance, you might be able to just do black box testing of saying that if I pass this information in, I should get this information out. So what does this mean in practice? I think that's important, right? So how many are familiar with Java util concurrent future? It's from Java 5. Cool. So I've written a fair number of implementations here. I think this is a great example. So let me just walk through how thinking about data might change how you would model something like this. So in this case, this is the get method. And when you create a feature, you're essentially saying that, hey, do this other work in concurrently with me, and I don't know when you're done, but when I need it, I will call this method, and I will wait for you to actually be done. So you could already be done, you could be done in the future, right? So it's a synchronization point. But when you get to the point where you need the information, you get this signature. So either it returns some value as a result of that computation, or it gives you an interrupted exception, an execution exception, or a timeout exception. So you have 4 different types of outcomes. And what this looks like in practice is something like this, right? If you need to consider yourself handling all of the cases, you have the typical return value you deal with as normal. But then there are 3 other result situations that you need to deal with as exceptions instead. All right, so if we think about this, right? So what we have is you can either have a success, you get your information, you get a failure because something went wrong, you get a timeout because it took too long, or something interrupted this thing. It just took too long, somebody wanted to shut that down. So we should be able to model this as a type itself, right? So it's 4 things that can happen. Let's introduce this async return type that has the return type as a part of its type parameter. So we would just declare this interface, async return, and the typical thing that we want, right, is we want to get the value out. So let's define some success type. So that's a record that has a single field, a single component. And then, of course, we have the failure case, and that has some sort of throwable. And it's not unusual for these failures to be some sort of business failure, right? Something happened that violated some domain rules. So we need to treat that separately from something else, like a timeout, which is more around, okay, so how is my application stable over time? Well, we need to have things time out if they take too long. But interestingly here, right, so this record type doesn't have any parameters. It's a record that has no structure but its name. So that means that all timeouts are equal all timeouts, which makes sense, right? It makes no difference if it's this instance of a timeout or that instance of a timeout, it's still the same thing. And then we have the interruption record, that is the same. It's a record without any components. So we have those four different, we have those permutations of return values. And then we add the ceiling information saying that, okay, so these are the only things that I'm aware of should be able to happen. And importantly, this is also information to the caller, saying that these are the only four different things that can happen here. So how do we use that? Well, now we get a async return out instead of an exception or interruption exception or something else. So there's no need for a try-catch block here anymore. And we can then switch over the value that we got. And we can now look at, okay, so what did I get? Well, we know that there are four different things that could happen, but now they're all treated the same. They're the same sort of abstraction that you use. You don't use a try in one case and you use the typical, I just got the value and I can just do whatever I want. So now there's a unified way of doing this, and you also have the ceiling information to say that, oh, you didn't consider the interruption here. Because what could happen is that if you call the original future get in a method that already declares throws something that is related to this, you might not even know that this specific operation I should deal with separately. Because now the compiler allows it because there was a throws clause already present. So this more localizes where you need to deal with the thing. So if you, like me, have been using Java for a long time, you know that the original switch was more of a C-style switch, that you switch over a number, and it's more like a dispatch table, right? But we have upgraded switch quite a bit and in different steps here. So now switches can be both statements and expressions. So you can assign the result of a switch to a variable. And you can switch over many things, not only integers, but also types, strings, enums, and there's this sort of the simpler version, which is an arrow switch, where if you only have one case or one action that happens as a result, you don't need braces and stuff like that. And you can now have patterns as case labels. So now you can say case, person, blah, 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 blah. And you can also add these guards, what we call guards, which is when clauses. So you can even be more specific, saying that case it's an integer, and that integer value is greater than 0. What we've also done is upgraded the switch for this ceiling information that I said before. More or richer exhaustiveness checking, which is always nice to know that did I consider all the cases. And it's pretty sophisticated, if I may say so. So some of the things that if you were to write the code as just ifs and elses, you wouldn't be able to necessarily reason about whether it's total or not. But the compiler would be able to reason about the totality in a different way. Also, as I said before, while default cases can be good in certain cases, no pun intended, it's also a source of unintentional bugs. So it's important to be careful about, is this likely to change in the future, and how do I know that it changed? All of this makes sense. So all of these features, records, pattern matching, being able to use switches differently, all come together to give you more capabilities than if you were only afforded one at a time. So while looking at new features, it's important to think, okay, so how does that relate to what else is in there? Because I think it's easy to say, okay, so you have a new for loop. I will use the for loop everywhere, right? That's not the intent, right? It's about being able to cover a broader set of possible applications and making it possible to do that easily, maintainably, and being able to learn and grow from that. And speaking of learning and growing, this might be, it was my first job application. I don't know about you, but it should be familiar. There's a lot of things that happen here, right? I heard somewhere that there is a rap song that teaches you all the different keywords that you need to do this. I haven't heard it, so I don't know. But looking at this as a beginner, not having written any program at all, there's a lot of things in there that you have to understand, right? And when you start out, you typically want to be able to do the bare minimum to do something. So having to do all of this to write your first Java program, really, it's unfortunate, right? So how about we instead try to have a more gradual experience where you learn step by step as you need more and more sophisticated functionality? Because if you look at this, all of the different things here do stuff, right? They have semantic meaning, and in order for you to know if it should be there or not, you have to understand what it is. And then you also need to understand, like main, that's a magic name. You have to know that main does something that non-main doesn't do. And system here, for instance, so that's a class, but it also has this static field out, which is not final, sort of. And so there's so many things that you need to understand in order to understand your first program. So let's look at the first program. What do we really need here? Well, we don't need the command line arguments, because you might not necessarily have used a command line before, so you might not even know what they are and what they're good for. So in this case, we don't need them, so why do you have to add them? And well, access control is nice, but what are we really trying to protect against here, right? It's fairly obvious that public doesn't really help anybody at this point. But also, do you really need to understand the difference between instance methods and static methods at this point? I'm not necessarily sure, right? And do we really need a class? Do we really need a class? Not really. It's sort of a static method that gets invoked from the outside, so it's not like the class is going to do anything here. So if we look at this program to see what you actually need to know, so void here is the return type. And it might be good to understand that you can produce something from a method. So void is something that you can explain, this thing doesn't really return anything. But when you need to, you can put something else there. And main, well, we need some sort of name for this thing. Otherwise, we wouldn't be able to call it from anywhere, because nobody would know what it was, what it would be. We need to be able to identify it in some way. So we end up with this as the smallest thing that you could write to have a functional Java program for the first time. What's interesting here, so this is, we have this in preview, and we're also working on implicit or being able to import entire modules specifically. So saying that I import everything public from this module. So instead of having to add like 30 different imports, you import the public members of the module. So while this might be, oh, so you're reducing the boilerplate, it's not necessarily about reducing what you have to write. It's about reducing what you need to understand at that point in time. So it's not about typing fewer characters. It's about what you need to understand at that point in time. And I think ultimately, simple programs should be simple. Do we agree? Is anyone that feels like that's unreasonable? I think that's a fairly reasonable thing, right? And if we can start with simple things, we can add complexity as we learn and grow. And I personally, I use JShell, the Java shell, every day for just anything really. Just what would this API call look like if I were to do it like this, or how do I do these things? So exploratory work. And writing scripts in Java is something that I do all the time, because I have these things that I'm experimenting with, and if I only need to change a small piece, then I would just rerun it. So I think, especially for educators, teaching other people to learn and understand Java, I think having this approach to how do you get started with Java in a way that isn't a completely different language. It's not about, oh, there's a different dialect. It's really about being able to grow your application as needed. So the paving the on-ramp is not about a different dialect of Java. It's still Java, it's all Java. It only reduces what you need to understand. And you can add those things. So if you're curious about what's going on there, have a look at that link. We have tons of stuff going through down the pipeline. And as I said before, preview is definitely the place you want to be if you're interested in providing input and thoughts into the process. As I said before, these are, when we put something out as preview, we consider them to be production quality. It's more about, we're not 100% sure that this is the thing that we want to move forward with in terms of the API. Should we change it? We need feedback to say, okay, you can do what you intended to do and it's not super confusing, right? So it's a window of opportunity for you to provide feedback. So lots of cool stuff in the pipeline. And as I said before, all of these things are a part of a much larger story. So it's not specifically about reconstruction expressions for records. It's about what does that enable you to do once you have that? How does that interplay with your pattern matching or your records in general? Like, how can I do stuff? How can I do builders or something like that? And also something that we're working on quite a bit is deconstruction patterns for classes. So how can you deconstruct classes, not only records or other things that have these sort of very rigid specifications on what they are. So lots of cool stuff coming. Catch me in the hallway after the session because I think we're just about out of time. So thank you all for showing up here in Malmö and have a great conference.